Okay, hi everyone. Thanks for coming out for the first theory seminar, I guess, in quite some time. I don't know when the last theory seminar was around, maybe I don't know.
I know, but I'm
sure. Two sort of like administrative announcements. One, you should sign up for the theory listserv if you haven't already done so. So it's theory at cs.brown.edu.
Theory at lists.
At lists. And it's on the slide by the elevators. Thing two is if you know anybody that might want to give a talk, you should encourage them to give a talk. We're still looking for more talks for the fall, starting in November. So I think we have like 3-ish slots left. Other than that, I think that's everything. Yeah. I'm very excited to introduce Ainesh Bakshi. He's a postdoc at MIT. He recently, 2 years ago, finished his PhD at Carnegie Mellon.
A year ago,
okay, yeah. He's still very young. He was advised by Pravesh Kathari and David Woodruff. He's done internships in several places, including TTIC and IBM Almaden. And at MIT, he works with Ankur Moitra and other people that I can read off of his website right now, but Sam Hopkins and Piotr Indyk. Yeah. So he's, I guess, worked quite a bit on sum of squares and like convex programming hierarchies, as well as algorithmic statistics and some numerical linear algebra things, as well as some quantum information theory, which I guess will be the topic of this talk today. So yeah, with that, I'll let you take it away.
All right, thanks, Ellis, for that generous introduction. No one really needed. I'll be talking about this recent line of work that I'm fairly excited about. It's called Learning Quantum Hamiltonians at Any Temperature and Polynomial Time. I don't expect any of this to make any sense yet, but hopefully we'll get through it. Feel free to stop me at any point and ask questions. This is supposed to be a talk that is directed towards a theoretical computer science audience, and that's all I'm assuming. So some linear algebra background, but that's it. Okay, this is a joint work with some wonderful people. Alan Liu, who's a grad student at MIT, Ankur Moitra, who's a professor at MIT, and Yuan Zhang, who's a postdoc at Berkeley. All right, let me start. By telling you what the outline of this talk is going to be, I'll start off with giving you some background on what a quantum Hamiltonian is. And the way I think of it is just linear algebra on really large matrices. Then I'll tell you the problem setup and why you should care about these problems. And I'll tell you the main result. And hopefully, till part 3, everyone follows everything. And then I'll give you an algorithm outline and some new ideas, which will be fairly technical. Okay. So let me start by telling you what a quantum Hamiltonian is. And you should think of this as an operator that corresponds to the energy of a system, of a quantum system. If this doesn't make any sense to you for now, just some motivation for this is this thing called the Schrödinger equation, which tells you how a quantum system evolves over time. So let's say you start off with some initial state, V0. This is just some vector in large dimensional space. This is what your quantum system starts out as, its initial conditions. And then it evolves for some time t. And at time t, the state is given by V0 multiplied by this matrix, which is e to the minus I ht. Okay. It's some transformation that is applied to the initial vector that tells you what the state of the system is at time t. The only important thing here is that this Hamiltonian h shows up in the exponent. So this is it's an important operator. It tells you what the energy of a system is. It's like one of the most fundamental objects in quantum information. So that's like the main object that we will be dealing with. This is the background for it. Let me actually tell you what this object is. It's just for a system of n particles. So if you have n starting particles, this Hamiltonian operator h is just a matrix, which is 2 to the n by 2 to the n. And the entries in this matrix are complex value. Okay, so this is what we'll think of the Hamiltonian being for this talk. Now this matrix H is not arbitrary. It encodes structure, and it also admits a concise description. So it's not like a dense matrix with no structure at all, but it actually has like a small polynomial size description. instead of this huge 2 to the n by 2 to the n description. Okay, so I'll tell you more about what this matrix is through an example. So the working example for the rest of this talk is the quantum generalization of this thing called an Ising model. Maybe you've come across this before. But if you haven't, it's just that your particles lie on a square grid. So they look like this. And each particle has at most 4 neighbors, which are these neighbors. Okay, so let's see what the Hamiltonian corresponding to this grid is. Let's begin by defining a graph. We love these objects. So you have a graph on vertices and edges. The vertices are each particle that is present here. And the edges are just the edges that are connecting these particles. So the degree of this graph is at most 4. And now this Hamiltonian operator that I was telling you about is just like a sum of terms. And each term corresponds to one edge on this square grid. So I can decompose a Hamiltonian into one Hamiltonian term, which is this H sub E. It's again a complex matrix. I'll tell you what it is. And a weight, which is called the interaction strength. So for each edge in this graph, let's say the edge 0, 1, I have H sub 0, 1, and I have lambda sub 0, 1. Okay? And this lambda is just a scalar quantity. Okay. Okay, so now let me tell you what this H sub E matrix is. This H sub E matrix basically acts on 2 particles or qubits at a time. So since there's an edge between S0 and S1 here, this matrix does is non-trivial only on the particle S0 and particle S1. Okay. Let me be a bit more precise. So let's say I'm looking at the edge, which is corresponding to the last node and the second to last node. And I've chosen this for convenience. And on these nodes, the matrices look like this funny matrix, which is almost identity, but I flipped the sign. This is what the matrix looks like on n-1, and on n-2, it looks like 0, 1, 1, 0. Okay, so these are 2 by 2 matrices on each particle, and then I've tensored them up using these Kronecker products to construct a matrix that actually lies into the n by 2 to the n. Okay, so this is a mouthful, so let's spend some time going through what is going on here. H sub E is a matrix that is in 2 to the n by 2 to the n dimensional space. But what I told you was this acts non-trivially only on the particles, only on the last and the second last particle. And non-trivially means that the matrix is not the identity on this particle. So these 2 matrices are not identity, and then I tensor them up with the identity matrix. Okay, does the definition of this 2 local Hamiltonian make sense? Yeah.
By tensor them up, you just mean change the dimension, right?
I mean the Kronecker product. I can define it for you. The Kronecker product of a matrix A, B. Let's say these are 2 by 2 matrices. So the Kronecker product is just the first entry times B, the second entry times B. Okay, and I just do this operation repeatedly. Yeah. Okay, here's a picture that might help you visualize what this Kronecker product does and how you get a huge matrix out of it. So let's say these last 2 matrices combined form the matrix X. This is some 4 by 4 matrix. And when I tensor this up with the identity, the resulting matrix is this block diagonal matrix where I have these 4 by 4 matrices which are all X along the diagonal, and all the off-diagonal entries are 0. Okay. Does that make sense for what the tensoring operation is doing? Okay. Great. If this Hamiltonian was acting on some other edge, which was not the last edge, you'd get a permutation of a matrix that looks like this. You just permute the rows and columns. But that's inconvenient to draw, which is why I picked this. Okay, any questions about what a Hamiltonian is now? So hopefully you get some intuition for what this huge object is. It's not arbitrary. It has this nice structure. It's permutations of block diagonal matrices. And each of them is scaled by scale. Yeah.
Is there intuition for how I should be trying to understand the way in which it acts on, in this case, the last 2 particles?
Excellent question. So let me go to the next slide. You can assume that the interactions on these particles that are non-trivial, which are not the identity, are just one of these 3 matrices. These are called Pauli matrices, they have a specific form. The particular form is not important. What is important is that they just form a basis for the 2x2 complex vector space of these matrices. Okay, so I can whatever matrix you have, you can decompose it as a linear combination of these Pauli matrices, and it suffices to think of them as just one of these. Yeah. Okay, and some other facts about these Pauli matrices: they are Hermitian, and they have real eigenvalues. Okay. Any other questions about the setup?
So we're saying each local Hamiltonian is a linear combination of them, or just one specific one?
Yeah, so you can, if each one of them is like a linear combination of a small number of them, you can just expand it out. Okay, so for now, just assume that each one is literally a Pauli operator. And you can take the coefficients and stick them in this constant interval. Great. Any other questions?
Sorry, I missed something. So if each HE here is a Pauli matrix, or it's a tensor of?
It's a tensor. So each HE here is a matrix in 2 to the n by 2 to the n dimensional space. And these Paulis are just 2 by 2. So they're acting non-trivially on 2 qubits or 2 particles, and then you tensor them with the identity in the right order on the rest.
I see.
And then you get a 2 to the n by 2 to the n matrix.
Right.
Just like here.
So it's always two non-identity Pauli matrices tensored with all identity matrices.
Correct. In this simplified model that I'm explaining, if this is indeed the case, you can consider generalizations of these where there are more than 2, they're acting on more than 2 particles at a time. But on this grid, there are only 2 at a time.
But identity is also a Pauli matrix.
Identity is also a Pauli matrix, but it does nothing to the particles. It's the trivial one. Yeah. Great. Any other questions? Yes.
How do you decide which Pauli matrices to tensor with?
This is what your quantum system's behavior is supposed to be. So the quantum system, in some sense, decides which one.
So it's not you know what Pauli matrices you have to act on that system?
Yeah, it depends what you know about your system. If you assume that you know what your system should behave like, then you can assume it's one of these, or it could be some. Yeah, we'll get to this. This is an important point. Okay. Okay, so if a Hamiltonian was clear, let me tell you about the next character that appears in the story, which is this thing called a Gibbs state. And the way physicists think about this is that it's the state of the system when it's achieved thermal equilibrium. If that means nothing to you, this matrix rho is another matrix in 2 to the n by 2 to the n complex dimensional space. And it's given by the following operation. So I take the exponential function, and in the exponent I have minus beta times h. So h is the Hamiltonian. This beta is just a scalar. It's called the inverse temperature. But for us, just think of it as a real valued scalar that is greater than 0. And then you divide this by another scalar, which is the trace of e to the minus beta h. Okay. So let me tell you a bit about what these operations are doing. This operation, e to the minus beta h, it takes the function f of z, which is e to the minus beta z, and applies it to each eigenvalue of h. Okay, this is what the matrix exponential function does. And the trace is just computing the partition function of this object. This is a fairly well-studied notion, partition function, but the reason we have it here is just so that this matrix is normalized, that its trace is equal to 1. Any questions about what a Gibbs state is?
So if you apply this on a vector of a state, it'll tell you the probability or equilibrium probability of being in that state.
I'm not sure what you mean. This is the equilibrium state in some sense.
Yeah.
You should not think of this as being applied to a vector.
Okay. Yeah.
Okay.
Actually, I am lost. Sorry,
Yeah.
I'm just staring.
We can wait.
So, can you just give the intuition? So, obviously, the higher the temperature, the more. Maybe that's not obvious. I don't know. What's the intuition behind it? Never mind the equation.
Oh, what's the intuition behind it? The intuition is that if you have a system and you let it just cool off, like in isolation. Whatever it like converges to, the interaction of the particles converge to, will be this.
And it does converge.
Yeah, if you let the system like just do its own thing for a while, eventually this will be the distribution that you would get. It's not convenient to think about it as a distribution, but the way I think about it, it's just some matrix. Where the matrix is, you started off with your Hamiltonian, and you applied the function e to the minus beta z to each eigenvalue.
Okay.
This is the abstraction we should think about and keep in mind. The physics interpretation of it's not so important.
Okay.
Yeah.
So if you put the Gibbs state into the Schrodinger's equation, is it just going to stay constant?
Yeah, it's what it converges to.
Even though it's the same Hamiltonian, it just stays constant.
Yeah. Yeah, it's like it stops evolving after this point.
Okay, because that answers another question I had earlier, and that was why does this finite matrix describe the state of the system in perpetuity? And it's because it sort of stabilizes.
Right. Like think of it as like the stable distribution for a Markov process. Okay, great questions. Okay, with that background in mind, let me tell you what the problem that we're interested in is and some motivation for it. The setup of this problem, which we call quantum Hamiltonian learning, is the following. You start off with your Hamiltonian, H, and it's a linear combination of these two local Hamiltonians, H sub e's, and the weights that are associated with each term are these lambda sub e's, and we'll normalize them so they're between -1 and 1. Okay, so you start off with this Hamiltonian, and then you have the Gibbs state, which is just e to the minus beta h normalized by the trace for some beta greater than 0. Okay, so let me tell you what the learning problem is. It might not seem like a learning problem initially, but I'll convince you that it is. So you start off with copies of the Gibbs state. Let's say you're given n copies of this Gibbs state. You're given what this beta parameter, this inverse temperature parameter is, and you're also given the underlying interaction graph G, which is just like what particles are connected to what other particles, just the 2D grid. And the goal is to learn these lambda sub e's from the copies of the Gibbs state. And the way you should think of this as a learning problem is that the copies of the Gibbs state are your samples from some random process. And you're trying to learn some parameters, which are the lambda e's.
But once you sample it, haven't you kind of disturbed the whole system? How do you get
You do. So you assume you have like independent copies of the Gibbs state. You can prepare your system multiple times. Each time you can do something with it and then repeat this process.
Does the graph have the information about each of the HE local Hamiltonians as well? Or are those unknown?
It does have so if you know the graph structure and you assume that each of the HEs are polys, then you basically have a representation for what each of the HEs are. Right? You know like which edges they're interacting on, it's a poly, you know which one it is. So for us, let's
you know which poly it is for each
for this talk, let's assume you know which one it is.
Okay.
And all you're trying to do is learn these like interaction strengths, which are the lambda e's. Okay. Does the problem setup make sense? This is an important slide, so I don't want to lose people on this one. I can even pause for questions.
So you're given one beta and the corresponding row?
So the beta is fixed,
Okay.
and then you get multiple copies of rows. So row 1, row 2, row 3, row 4, and so on. You think of rows as your samples, and you're trying to learn the parameters, which are the lambdas.
Or why do I have multiple? Is a row fixed given beta and the graph?
Right, but when you do something with row, it will disappear. Like I'll tell you next. Yeah.
Okay, yep.
Yeah. It's like the way the model works. You can use one sample to estimate one quantity, and then you need a new sample. Yeah.
So do we have multiple betas or just
The beta is fixed. The beta is fixed. We know what it is. It's a fixed scalar quantity. Yeah. It's only that these rows are changing. Like you get multiple copies of them.
The row is kind of a distribution, or is it how should I think about it?
You can think of it as a distribution. It's not really a distribution. It's just this matrix. Like the matrix has this property that the eigenvalue is sum to 1, and it's PSD. So you can maybe think of it as a matrix, as a probability distribution. But
If I get a state out of it, do I get a matrix? What do I get?
great. So how do you interact with this row is your question. I will tell you like the interaction
Oh, okay.
very soon. Actually, we might wait a while for me to get to how you interact with this row. But let me tell you why you should care about the problem first.
Okay.
I promise I will eventually tell you how to interact with works. Okay, so this problem of learning a quantum Hamiltonian is a generalization of this really well-studied problem in learning theory called learning exponential families and learning graphical models. And there's been decades of work on understanding different aspects of this problem, including sample complexity, getting efficient algorithms, understanding phase transitions, and so on. One highlight in this area has been Parizzi's mean field theory of spin glasses. What is really striking about this is that the Nobel Prize in Physics in 2021 was awarded for some of this work. So even in the classical setting, this problem is very rich, and we're trying to understand the quantum generalization. And I believe that the theoretical landscape of this problem in the quantum world should be at least as rich as it was in the classical world. So lots of work to be done here. Okay, so that's the first motivation. Another motivation for this is building near-term quantum devices. So let's say someone comes to you and says, I want to build a quantum computer. Well, what they start off with is like a desired Hamiltonian that they want to implement. And you can use this like a solution to this learning problem as a way to certify that your device is implementing the Hamiltonian that you desire by learning the interaction strands. And this is hard to simulate classically. So like if you have more than 100 qubits or something, you cannot simulate these Hamiltonians classically.
Are the Gibbs states uniquely defined by the Hamiltonian, or?
They're defined by the Hamiltonian and this beta parameter.
Okay, yeah. But are they, I guess, unique? Like if you're trying to certify that you have some Hamiltonian, it suffices to just learn what the beta is a Gibbs state of it.
Well, we'll show you how to solve this problem from the result is going to be that from the Gibbs state, you can learn the parameters of the Hamiltonian. Okay. That's the problem, right? So if we succeed in solving the problem, then you can indeed do this certification. Okay. And finally, this is also used to understand topological order and design experiments and understand phase transitions of Hamiltonians that we don't analytically understand, like the 2D Fermi-Hubbard model. Let's not worry about it. There are some applications people like that. Full disclosure, I don't particularly understand these applications either. I'm like a theoretical computer scientist, but I was told that these are applications. So all right, let's move on. And let's go back to things I do understand. So I'll tell you my prior work on this problem. And there is this really nice paper by Anshu, Arunachalam, Kuwahara, and Solin Manifar that show that polynomially many copies of the Gibbs state suffice to learn the parameters, at least information theoretically. So if you had polynomially many copies, you can learn these lambdas up to your desired accuracy. But the drawback of this result is that it's computationally intractable, since the estimator that they have requires computing the partition function, which is this trace quantity that I alluded to earlier. And we know that computing the partition function, even classically, is a sharp p-hard problem. It's like harder than NP. Okay, so this approach is really computationally intractable, but at least it tells you that if you have a polynomially many number of samples, you can solve the problem. Okay, what else? So there was a follow-up work by Hao, Kothari, and Tang that showed that when this temperature parameter beta is less than a constant, the critical temperature, which is known as beta sub c, think of it as like 1 over 1,000 or something, then there's a polynomial time algorithm, and it requires only polynomially many number of samples. Okay, so in this regime where beta is small, this is called the high temperature regime, since beta is inverse temperature, you can learn efficiently. Okay, any questions about prior work? Yes?
Is that the beta C that corresponds to the transition to paramagnetism?
Yeah, it's like similar to the critical temperature at which you see a phase transition, I think. Yeah. Okay. So what's the central question that we were interested in? The question was, is there an efficient algorithm for learning a quantum Hamiltonian at low temperature when beta is large? So we don't want to presume that beta is a tiny constant. Can we learn it for any beta? Okay, and we were not the first people to ask this question. Here's a survey by Alhambra, which asks the same question. And it says that, in the high temperature regime, we have tight sample complexity and running time bounds. But beyond that, like our theoretical understanding is incomplete, and it also mentions some of the applications I was telling you earlier. Okay. Jason? Yeah.
Was the algorithm classical algorithm? Or
No, the algorithm is actually quantum.
Oh.
And our algorithm will also be quantum.
Oh.
But it will use quantumness in like a minimal way. Like we'll just do one step that is quantum, and then the rest of it will be entirely classical. Yeah. Okay. And there was another survey by Anshu and Arunachalam, which also asked the same question: can you learn this efficiently for arbitrary beta? Okay, so the point I'm trying to get across is that this problem, there has been a lot of interest in it in the quantum community, and they really wanted to know whether there is an efficient algorithm or not. And why is this problem hard? Well, there are these existing approaches which correspond to estimating the partition function in this first paper, an approximate Markov property, which is a generalization of the way we solve the classical version of this problem, the learning exponential families, and this last thing, which is called cluster expansion. I don't expect you to understand what these terms mean. All I want to get across is that all these approaches we can show that they provably fail when beta is large enough. So we really need like a new approach to solve this problem. Okay, are there any questions about the setup and the central question that we're asking? Yeah.
Is there intuition for why it's harder to learn at lower temperatures?
Yeah, the intuition is essentially coming from the fact that all these things stop holding. So like if beta was sufficiently small in certain regimes, you could estimate the partition function efficiently. When beta is large, you cannot do this. And the same thing starts holding for the rest of the property, like the rest of these conditions. So like a Markov property will stop holding when beta is large. It's just that there's like more disorder in the system. I don't know. This is vague intuition. I don't really know.
I guess you mentioned that estimating or maybe exactly computing the partition function is structurally hard.
Yeah.
Do we have classical hardness for this problem, or in theories could one like maybe do away with the?
Wait, what do you mean by classical?
As in is there a possibility for a non-quantum polynomial time algorithm for this?
Oh, this is hard classically too.
Okay.
Yeah, even like the classical Hamiltonian computing a partition function is hard. In fact, like this was like one of the problems that Valiant introduced as the sharply hard problem.
Okay.
Corresponds to counting things.
Okay.
So for these existing approaches where the B is small.
Sorry, I can't hear you.
So for the existing approaches where B is small,
Yeah.
so high temperatures,
Yeah.
they're all classic approaches, right? Classic.
No, these are all quantum algorithms.
All of them.
Yeah.
Okay.
Yeah, I'll get to why that is like in a bit. Hopefully, it'll be clear why these need to be quantum. Other questions? Yeah.
And just so the Gibbs state's thermal equilibrium, and beta is the temperature that thing is when it is at thermal equilibrium?
Yeah, but you really shouldn't think of this as like the physical temperature. It's like some other parameter that corresponds to temperature, somewhat loosely.
Oh.
Yeah.
But the idea is that it's, I guess to motivate it, we would want lower temperature. Is it true that we want to motivate it because we want lower temperatures because it's hard to keep things hot, or is that just completely...
So the reason why you want low temperature is because these interesting macroscopic phenomena like superconductivity, etc., happen when the temperature is low. And the reason for this is that once you're low enough, there are long-range correlations between these particles. So initially, the particles are only interacting with their neighbors. But if you want to see some macroscopic phenomena like superfluidity or conductivity, you want these like short-range correlations to act together and like show some like large-scale phenomena. In the statistics language, it would mean like you want correlations to not decay, and this is what happens when beta is large, which is, I guess, some more intuition for why this is hard. Like even classically, it's hard when correlations do not decay. Okay.
Sorry.
Yeah.
So it might be helpful to elaborate on the case where beta is very, very large. Then this is like learning the minimum eigenvalue component of H.
Right, but for that,
Is that the long range thing?
I want to skip that. Maybe we can take that offline.
Okay,
It doesn't really match with the rest of the intuition. Okay, let me move on in the interest of time. Let me tell you what our main result is. The informal statement of our main result is that there is a polynomial time algorithm that requires polynomially many copies of the Gibbs state at any temperature beta, and it learns the interactions of this. It learns the lambdas of this local Hamiltonian. Okay. So this is the informal statement. Let me be a bit more precise.
Sorry, why does it contradict the other one that says that it's hard?
What is hard?
You said that.
Estimating the partition function is hard.
Wait, didn't you say that if there are no restrictions on beta, then it doesn't work? Then it's computationally hard. It cannot be followed.
Right. So
So
computing.
what's the trick?
Right. So computing this trace quantity, which is the partition function, is
Learning
hard.
lambda e.
Oh, I see. So the other algorithm required that, and that's hard. And
Yes.
now your algorithm doesn't require that. Okay.
Precisely.
That's it.
Precisely. Our approach will avoid estimating the partition function whatsoever.
Okay.
So let me be a bit more precise about what this theorem says. You're given m copies of this Gibbs state at some beta, and you're given an accuracy parameter epsilon, and you output estimates, which are these lambda e hats, such that each one is close to the corresponding true interaction strength up to epsilon. The sample complexity, which is the number of copies of the Gibbs state, is polynomial in the number of particles, and doubly exponential in this beta parameter. So the algorithm for really large beta is like really, really bad. And the running time is polynomial in the number of samples. So if you have m samples, then the running time is just m to the power, maybe 10 or something.
Was the previous just sample complexity result also doubly exponential on beta?
It was not. It was not. But you can show that a single exponential dependence on beta is necessary, even possibly. And this doubly exponential dependence on beta, we don't know whether this is the price of efficient algorithms or not. It's an open question to try to improve it to singly exponential. Yeah. Okay, so this is the main result. I hope it makes sense. If there are any questions, I'm happy to spend some time on this slide explaining what the result means.
Is there any assumption on the range of lambda e?
So I assumed I normalized them to be between plus minus 1, which is why this additive or epsilon is the right scaling. Yeah.
So you said that the single exponential dependency on beta is necessary,
Yes.
but the other algorithm only had polynomial number of samples. So how does that?
So polynomial in n, so it's always
see, but it's
polynomial
still
in n, but
exponential in
exponential in beta. So 2 to the beta. Yeah. Yeah. Yeah.
So this is kind of bad for low temperatures. No, for
It's
high
actually
temperatures, for high
improving.
temperatures.
It's actually improving when beta is small,
Yeah, okay.
but it
Which
won't
is high
improve too far.
temperatures.
Yeah. Okay, so this works for any beta. More questions, or should I move on? Right, I'll move on. So now let me get into the technical parts of how you interact with the state, etc., and what is the model of computation. I'm going to black box most of how you interact with the state, and what we'll assume is that we have access to this quantum magic box, and you take your Gibbs state rho and some local Hamiltonian HE, and you put it in this box. And the thing that you get out of the box is this scalar quantity, which is trace of HE with rho. Okay, so this is an exponential size object. This is an exponential size object. We can't really work with them if we are polynomially bounded, right? So what we do is how we interact with this input is that we're allowed to measure things of this form. We're allowed to measure trace of HE times rho. And we can do this for any term. It doesn't have to be just HE. We can do this for any local operator that we care to design. Okay, so this is how we're interacting with this state, and this magic box is a quantum computer. Yeah.
So what is this complexity bounded by when you put it through the quantum magic box?
So I'm assuming you can do this in constant time. You get one of these as the primitive operation, and then we're trying to understand how long it takes to solve the problem given access to such a box. Yeah. But in reality, if you wanted to estimate this quantity up to additive error epsilon, then you would need like 1 over epsilon squared copies or steps or queries to this box.
So are you assuming you know HE, you know which two Pauli matrices HE should be, or are there like inside each term in the sum there's 9 possible tensor products?
So for this talk, let's assume you know exactly which one it is. And in this model, like this black box model, I can query any local Hamiltonian. It doesn't necessarily have to be the terms that appear here. Like I don't have to just query the HEs. I'm not restricted by this. I can query whatever I like. Okay. Does that access model make sense now? Does that answer your previous question about? Okay, so let me tell you a bit of how the previous argument works, this information theoretic argument. Let's say you have two Hamiltonians, H, which is summation lambda E HE, and H prime, which is a different set of weights, but the same terms. So you have lambda E primes, but the same HEs. And the corresponding Gibbs state rho and rho prime. Okay. What this argument says is if you perform the following measurement through the black box that I just showed, you measure each of the HE rows and HE rho primes, and you look at the trace. And you insist that these two traces are equal. So you say that the trace of HE rho and HE rho prime are the same for each of the terms in the Hamiltonian, so for each of these HEs. Then the lambdas must be equal. It's saying like if I match these traces for each of the terms, then the underlying parameters must be the same. Okay. So in some sense, it like suffices to match these trace quantities that we've computed. Does this make sense? Any questions about this? Okay, so let me give you like a different spin on what this result is saying through the lens of constraint systems. Instead of just matching these like terms for two Hamiltonians, what we'll try to do is write a search problem and try to find the parameters of this search problem. Okay, so now think of these lambda E primes as variables. These are the variables that you're trying to find. They should correspond to the true lambdas. Okay, so what can we know? What do we know about these lambda primes? Well, let's begin by just defining the corresponding Hamiltonian. This is just a linear combination of HEs. Now this H prime is a variable. I'm trying to find some Hamiltonian that corresponds to these lambda primes. Okay, we also know that the true lambdas are between +1 and -1. So I can add this as a constraint too. Okay. And finally, I can add in the constraint that the trace with respect to HE of rho, which I can compute through measurements, like I saw on the previous slide, is equal to the trace of HE with my variable that I measured. So I created this variable H prime, and I look at the matrix e to the minus beta H prime. This is again a matrix of variables. I can write down the trace inner product with HE, and I can normalize it, and I can ask, find me lambdas that satisfy all these constraints. Okay. Now this constraint system is like impossibly hard to actually solve because it has like matrix exponentials running in them, and even polynomial systems are hard to solve. But at least it tells you like a framework for how to think about it through the lens of constraint systems. And then we'll spend the rest of the talk trying to like modify this constraint system into one that you can solve efficiently. But let's start with this one. So if you reinterpret this result by Anshu et al., the result says that if you manage to solve this constraint system, then any approximate solution will be close to the true parameters. So that's quite nice. At least the constraint system is well defined. Okay, but as we know that solving this constraint system is hard. So now we have to modify the constraint system. But okay, are there any questions about what this system is trying to do? Yes?
Sorry, you mentioned this. Can you speak a little bit to the last constraint and like why this is a constraint that makes sense? It's not just matching traces anymore.
So why does this constraint make sense?
Yeah.
Okay, so let's look at, so think of what you want H prime to be. You want it to be H, right? So this guy here is just trace HE e to the minus beta h over trace e to the minus beta h.
Oh, sorry. Yeah.
Okay? And the right hand side is exactly the same thing with h prime instead of h. Yeah. If you want to be more concise, this is trace of HE rho prime, where rho prime is the corresponding variable Gibbs diff. Okay. So what is the high-level approach that we take? Instead of just measuring the trace of these local operators HE, we'll measure a larger set of operators, since our model allows us to do that anyway. Okay. And then we'll take these measurements and enforce additional constraints that are satisfied by the true lambda keys. Okay, this is only making the problem harder. I'm adding in extra constraints. The next thing that we'll do is we'll try to approximate the exponentials using low-degree polynomials. And once we do this, we'll have like a system of polynomial inequalities. And we'll try to solve a convex relaxation of this system. Okay, that's a mouthful, but let's start with step 1 and see how far we get. Okay, so step 1 was to measure a larger set of local operators and introduce extra constraints. The constraint that we introduced is the following. So now instead of just one HE term, we have two terms. So we have X and Y. These are some local operators. They don't have to be two local anymore. They can be like 100 local or something. And for each one of them, you match the traces. So you look at trace of Y, e to the minus beta H prime, X, e to the beta H prime rho. And you set it to be X, Y rho. Okay. Now this might seem like a constraint pulled out of nowhere. So why would you want to do something like this? Well, I don't have like amazing intuition for why you should do this, apart from that this constraint is satisfied by the true parameters. So let me show that. So like, if you set h prime to be h, then this kind of constraint will be true. And let's work through this. It's a nice exercise. So let's say you plug in h prime equals h. Right? And then you substitute what rho is. So rho is just e to the minus beta h. This term and this term cancel out. They do 1. And then I can use the cyclicity of the trace to move the x here. So I get x, y, and then I have the only thing that's remaining is e to the minus beta h divided by trace of e to the minus beta h, which is rho again. So just using the cyclicity property of the trace and the definition, I know that this constraint is at least satisfied by the true h. Okay. So why not add it to the constraint system? Okay. The crux of the paper is to show that you can take these exponential constraints, which are of a different form now. So you have e to the minus beta h, e to the beta h on two sides of this local operator, and approximate this quantity by a low-degree polynomial in these variables lambda prime. Okay. Now, for technical reasons, it turns out that this kind of expression admits a low-degree approximation, whereas the previous one, where I only had like a single exponential, does not admit a low-degree approximation, which is why we work with constraints of this form. Okay, yeah.
Do the local operators have to be constant local, or can they be? Yeah.
The locality will depend on beta. In fact, it will be like 2 to the beta local.
Okay.
Yeah. But if beta is a constant, this is a constant. And you kind of pay in running time if you want to estimate these quantities.
I might be missing something. So why are you having 2 local operators instead of 1?
Yeah. If you have a single local operator, again, you run into this issue where the resulting expression, we don't know how to approximate it by a low-degree polynomial. So the only kinds of expressions that we can approximate by low-degree polynomials are expressions of this kind, where you have like y, and like it really needs to be of this particular form. Like if I had 30 more minutes, I could explain why this particular form is important. But
like both of them are local operators.
Yeah.
But they together become non-local.
Okay, great. So it turns out that this quantity cannot be approximated by a local operator, like anything local. It's like in poorly behaved, it's like exploding, even in like 2 dimensions. But what we show is that if you multiply on the left by this y and on the right by rho, you can control this quantity using just local things. I wish I could give you more intuition for why this is the case, but I don't really know. Like all I can tell you is that the math works. Yeah, this constraint is a bit mysterious. We don't really understand why it works.
I'm going to ask a very uninformed question, which is like, why 2 local operators? If you go to 3, can you not estimate this with a Degree polynomial? Or
the 2 local is not important. The 2 was just a modeling assumption because I was working with the 2D grid. You can do this for any k local.
Okay.
Yeah. It's just that you have to go and measure like something which is like more local than the thing that you started with. So if you started with like a 10 local HE, then you have to go to like 1,000 local. Yeah.
By like k local is just that how many qubits it depends on?
Yes. Okay, I have some vague intuition for what is going on in this constraint, but like ask me offline about it. Okay, I'm gonna skip the next couple of slides in the interest of time, and I'm just gonna focus on something classical, which is these polynomial approximations that I was alluding to earlier. So what we can show is that if you wanted to approximate the constraints in the last slide by low degree polynomials, it suffices to focus on the following classical question about approximating the exponential. Okay, so we call this a flat approximation to the exponential, and the challenge is just the following. So let's say you have some polynomial p, you want it to be low degree, and you want it to satisfy the following criteria. You want p of c to be close to e to the minus beta z, so epsilon close, everywhere in the interval -1 to 1. Okay, so you have an interval -1 to 1. In this interval, you want to be very close to the exponential. Okay. And the second constraint is that outside this interval, you want your polynomial to not explode too quickly. Like you don't want the growth to be more than e to the 0.1 times the absolute value of z, let's say. Okay, and if you're familiar with like classical results in polynomial approximation theory, this first kind of guarantee is really well understood. Like we really understand how to approximate like functions in a bounded interval. You can do this using Chebyshev polynomials. If you've heard of that. But the really challenging part of this setup is that we don't know how to control the growth of these polynomials outside this bounded interval. And this part is like really crucial for approximating the constraint with a low degree polynomial. You really need this second part. Okay, so what we show is that if you had such an approximation, this like flat approximation of the exponential, then the constraint that I showed, like this trace e to the minus beta x e to the beta rho, can be approximated by a low degree polynomial in the lambdas. Okay, and we only know this approximation to hold when the left side has this particular form, like y e x e rho, and it kind of breaks down when you don't. Okay. Let me also say that like some standard things that you would try to construct such a polynomial approximation of the exponential do not work. So if you start off with the Taylor series expansion of the exponential and you truncate it after some number of terms, you can show that you need to go like really far and like basically need to collect like n terms for this approximation to be valid. And the same holds for Chebyshev polynomials. You can't satisfy the second guarantee. Like this is a guarantee that's hard to satisfy. You can't do this with either a Taylor series truncation or Chebyshev polynomials. Okay, so let me tell you what our key idea for constructing this flat approximation is. And the idea is to like peel the exponential. So we have e to the minus beta z for some large beta. We can write this as e to the minus beta c for some small constant. So this beta c is again this critical temperature, and it's like a small constant. Think of it as like 1 over 1,000. And I have like beta over beta c terms, where each one of the terms is the same, so I just multiply them out together. What is nice about writing the exponential this way is that each of these terms where the exponent is a super small constant, you can approximate it by a Taylor series. Yeah.
Is this motivated by like a divide and conquer approach?
It's not really a divide and conquer approach, but there is like some moral similarity where you want to, treat these terms independently. So like you are kind of dividing it into these like different blocks. And the way you want to treat them independently is that you don't want the approximations to interfere with each other. So your Taylor approximation that we construct, we truncate it at like different degrees so that they don't interact with each other. This is also what leads to like exponential dependence, like doubly exponential dependence on beta. Yeah. This is like the vague intuition for what is going on. Let me show you a picture instead. So I was on Twitter yesterday, and someone on Twitter had implemented our polynomial approximation, which was convenient, so I took it and I cited them. This is what the Taylor approximation in blue, this is what Taylor approximation looks like. And this orange and green approximations are what our approximation looks like. And to satisfy the second constraint, note that we have to be like below the exponential. We wanted the growth outside this bounded interval to be small. And you can see that the Taylor approximation, like somewhere after like -10 or something, is exploding much faster than our approximation. So, thanks to this person, you can see a picture of our approximation. Okay. Any questions about what this statement is? I don't have time to give you the proof, but this is at least what the picture of our approximation looks like. Okay. Let me tell you a statement about the degree of this approximation. So what we ended up showing is that there is such an approximation that has degree 2 to the beta plus log 1 or epsilon, for this being epsilon equals everywhere. This 2 to the beta is what goes in the exponent of our algorithm. So once you have these like low degree approximations, this is what goes in the exponent of the running time. So if you could improve this approximation to just polynomial in beta, you get a faster algorithm. Okay, so let's put it,
Are each of the Taylor expansions for each of the like field exponentials costing you 2 to the beta, or is the beta from the number of the beta over beta c?
It's coming from both. So each of them are like this degree, and the reason why they have to be of this degree is that we're like geometrically increasing the scale of where we are truncating them so that their tails don't intersect.
Okay, so it's not the same truncation.
It's not the same truncation. Each truncation is different. It's like designed so that the first truncation doesn't interact with the second one doesn't interact with the third one, and so on. If you want to do this for a polynomially many number of things, then you have to set the scale to be exponential. Okay. Other questions? Okay. If not, let me put it together and say where this was all heading. So we had some constraints that we started out with, which looked like exponentials. Then we saw these polynomial approximations to the exponential, which we were calling these flat approximations. You can use these flat approximations to go back and replace the exponential constraints with constraints that are just low degree polynomials in these h primes. Okay, now this resulting system, we're still trying to search for these variables lambda prime, but instead of satisfying an exponential constraint as the last constraint, we've replaced it by a polynomial constraint. So you might say, what progress have you made? You started off with something that was hard to compute, and you replaced it by a polynomial. The polynomial system is also hard to compute, so apparently it might seem that there has been no further progress. But what you can do is you can solve a convex relaxation of a polynomial system. The one that we decide to solve is this thing called the sum of squares relaxation. It's just like a convex relaxation. You can write it down for any polynomial system. And the major technical bulk of the paper goes into analyzing that if you solve this convex relaxation, you can round the solution to an actual accurate estimate of the true parameters. So that's the bulk of the technical argument. The conceptual part was getting from exponential expressions to polynomial expressions. Okay. I won't be able to tell you how sum of squares works, but catch me later and I could try to give you some high-level overview. All right, let me end with some takeaways and future directions. Turns out that modern tools in optimization, like solving the sum of squares relaxation, led to this resolution of learning Hamiltonians at low temperature, which is quite interesting. A follow-up question would be when can we cast quantum problems in general as systems of polynomial inequalities? You get these exponential expressions to begin with, but sometimes, as we saw, you can replace them with low-degree polynomials. And of course, the technical question here is, can we improve the doubly exponential dependence on beta to something seemingly exponential, or prove that it is necessary if you want an efficient algorithm? Okay, I'll stop here. Thank you.
Okay, we have time for maybe one or two questions from the audience. Yes.
Yeah, I've read a couple of Tane's papers and such, and it seems that a lot of the focus is actually proving that a lot of classical algorithms, quantum doesn't provide as beta one classical algorithms. So how can we be sure that there isn't a classical version? Could you say a little bit more about that?
Sure. Yeah. So the question for those who couldn't hear it is a lot of work that my co-author did was to take these quantum algorithms and show that there are classical algorithms that can match the performance of these quantum algorithms. I can't completely rule out the possibility of a classical algorithm doing something like this, but every single object that I told you about, the Gibbs state, the Hamiltonian, etc., are objects that are 2 to the n by 2 to the n matrices. So I can't even write them down or tell you a description of at least the Gibbs state, which is concise. So if I have to interact with these objects in some meaningful way, I think I need access to some notion of quantum computation. So I don't even know what the classical model here would be. And if you try to actually simulate these systems classically, just simulating a Hamiltonian classically, we know that this is actually hard after 100 qubits. So I don't suspect a classical algorithm for this anytime soon.
Isn't there didn't you say that they were polynomial size descriptions of these things?
Of the HEs, yes.
Of the HEs.
But I don't know one of the Gibbs states.
I see. Yeah. Okay. More questions? One more question.
Can you repeat, when you were describing that polynomial that satisfies two conditions, how does that fit into the main problem again?
Right. Okay. So the question is, how does a polynomial approximation fit into the main problem? So the way it fits is that if you had such an approximation, you could take this expression, which is an exponential in the h prime. So it's e to the minus beta h prime, x e to the beta h prime. And you can replace this thing, which is an exponential, with a low-degree polynomial by applying this polynomial b to some matrices. I won't get into exactly what matrices. It's a bit technical. You have to define these things called commuters. But there is a one-to-one correspondence between these polynomials and matrices. And if you could construct such a polynomial, you could approximate this constraint, which is an exponential, by something which is way nicer to deal with, is a low-degree polynomial.
Thank you.
Yeah.
Okay, let's thank Ainesh one more time. If any of you want to meet with him, he also has slots that you can sign